For decades, the popular image of a deep dive investigation has been the detective's corkboard, a wall covered in pushpins and red string used to map the physical links between evidence. That spatial mapping might work for a single, isolated crime, but it collapses completely when applied to the scale of modern intelligence gathering. Today's open-source intelligence analysts aren't handed neatly curated folders. They're hit with massive data dumps, hundreds of gigabytes of files released all at once. These caches are messy: 30-year-old court records, hastily scribbled handwritten notes, thousands of internal emails, and hours of raw audio. A human team cannot manually read, cross-reference, and catalog a 100-gigabyte dump of this nature. The math simply does not allow it. An analyst would spend years just reading the material, long before any actual synthesis could begin. In modern investigations, acquiring the data is rarely the final hurdle. The true bottleneck is processing all of that unstructured data into something a human can actually query and understand. In 2019, the Boston Globe launched an investigation called Blind Spot, aiming to uncover the systemic regulatory failures that were enabling deadly highway crashes. Around the same time, reporters at the Tampa Bay Times were working on a project called Poisoned, exposing severe, localized toxic lead exposure occurring at a Florida smelting factory. Both investigative teams faced the same immediate roadblock. They had successfully obtained thousands of pages of obscure, unstructured agency documents and logs, but no efficient way to read them all. To break through the noise, both teams utilized Google Pinpoint, a research tool designed specifically to ingest massive collections of documents and extract the metadata inside them. By applying AI pipelines to unstructured data, researchers can reorganize chaotic dumps of raw files into structured, queryable entity graphs. The first phase of this AI pipeline is bulk ingestion and data normalization. When raw files are uploaded, document AI algorithms scan for text using optical character recognition. They parse lossy image formats and highly degraded, decades-old scanned court documents, converting the pixels into clean, machine-readable text. For this text extraction to be highly accurate, the source documents generally need to meet a specific technical threshold, ideally scanned at a minimum of 200 to 300 dots per inch. The ingestion process extends to audio files as well. The system runs speech-to-text algorithms capable of automatically detecting and transcribing over 100 different spoken languages. The output of this audio processing is a searchable PDF transcript, permanently tethered to the original audio file through hyperlinked timestamps. By the end of the ingestion phase, the software has eliminated the file format barriers, rendering all the disparate evidence into a single searchable digital baseline. The pipeline then moves into its second phase, elevating basic text search into automated entity extraction. Natural language processing parses the text to identify and categorize specific nouns, people, organizations, and locations. It strips these entities from paragraphs to generate a navigable index list of every major player and place. This creates a massive interconnected entity graph spanning the entire dataset. NLP entity extraction constructs a relational database from the linguistic patterns in the text. Instead of manually reading thousands of pages to identify a single connection, researchers can track those complex relationships across decades of files. The final phase of the pipeline is advanced semantic querying. Semantic search understands the underlying concept of a query, rather than just matching exact character strings. This allows the search function to branch out to find synonyms automatically. This conceptual mapping also enables cross-language searches. An investigator typing a query in English will automatically surface matches in Spanish, French, or any other supported language present in the files. By combining the entity filters with semantic search, investigators can interrogate their dataset as a comprehensive ecosystem, drilling down into specific intersections of people, places, and topics. Structured querying redefines the researcher's analytical scope. The focus shifts from locating a single specific record to analyzing the statistical composition of the entire dataset. We can see this methodology in action with the Boston Globe's Blind Spot investigation. Reporters took the raw data they gathered from multiple, disparate state motor vehicle registries and ran it through the software to generate a unified index. This animated diagram illustrates what the journalists found: disconnected clusters of data. The software proved a severe lack of communication, showing that state agencies were failing to alert each other about their most dangerous drivers. Identifying this kind of negative space proving what is systematically missing from a dataset, is functionally impossible to do at scale without a machine-generated entity graph. The tangible outcomes of these investigations are significant. The Boston Globe's work prompted widespread legislative reforms and won a Pulitzer Prize, while the Tampa Bay Times investigation triggered a $319,000 OSHA fine against the offending factory. However, the technology has hard limitations. It cannot verify physical facts, it cannot conduct human interviews, and it feels no moral outrage. To actually build their story, the Tampa Bay Times reporters still relied on traditional journalism, hitting the pavement and ultimately interviewing over 100 workers to contextualize all the data they had parsed. AI tools like Pinpoint set a new analytical baseline by handling the computational brute work. This clears the desk, freeing the professional investigator to analyze the macro patterns and do what they do best: hold powerful systems accountable.